Hello students. So up until last class we looked into comparison test and examples involving comparison test. There are a couple of more tests in the context of improper integral, where we use them to talk about the convergence of those improper integral. So I believe we have covered sufficient examples on comparison test, and you will be able to work out few more examples in your assignment. And today we will start with mu test. So, test of convergence using mu test. So, the mu test for convergence. So, the statement goes like this: let f x be an integrable function for x greater than a, then integral from a to infinity f x dx converges if limit x goes to infinity x to the power mu f x equals to lambda for mu greater than 1, and integral from a to infinity f x dx diverges if limit x goes to infinity x to the power mu f x equals to lambda, which is non-zero, or plus minus infinity if mu is, or for mu is less than or equal to 1. So, for mu. So, if mu is greater than 1, then we can say that for this limit, then we can say that the given integral, improper integral, is convergent. If it is not, if mu is less or equal to 1, but we are still getting the finite value, then in that case the given integral is divergent. So, let us see a few examples where we can talk about the convergence of the given improper integral. So, example 1. Example 1, test. So, let's consider the similar example. So, test the convergence of 0 to infinity. Let us say we have cos x, by 1 plus x square dx. So, then in that case we can write it. So, the solution. So, let f x equals to cos x by 1 plus x square, and if I take limit x goes to infinity x to the power mu f x, then this will be limit x goes to infinity x to the power mu times cos x by 1 plus x square, and if I take mu as greater than 2, or how to say, at least mu equals to 2, then in that case this whole thing will be equal to 1. So, if I take mu equals to 2, so let us say if I take mu equals to 2, x cos x by 1 plus x square for mu equals to 2, then in that case I can be able to write this as 1 by so this is basically 1 by 1 plus x square times cos x, and this whole thing x square times f x, and this whole thing would converge to, or for the time being, if I assume that instead of cos x, if I let us say just start with just to make the example a little bit simpler, because I do not want to complicate it. So, let us start with just 1 instead of cos x. If I take just 1, then what would happen? Then if I take 1 here, let us say instead of cos x I have 1, then it will be a little bit straightforward. So, instead of cos x, let us say I have 1. So, then in that case this will be 1 by 1 plus x square, and then the whole limit will be 1 for mu equals to 2. So, the message which I want to convey is limit x goes to infinity, x to the power mu f x is equals to a lambda which is basically our 1 for mu is equals to 2, which is greater than 1. So, having this limit here, which is of course finite, for mu is equals to 2, which is of course greater than 1, we can be able to apply this mu test. So, I just wanted to show you with a simple example. So, having cos x would complicate a little bit. So, let us not go there first of all. So, if I have 1 by 1 plus x square, we have already worked out this example several times, but I would like to show the application of mu test here. So, let us say you have the integral, improper integral of this type. So, we multiply by x to the power mu to the function f x, and then I am evaluating this limit. So, if I choose x equals to mu equals to 2, which is greater than 1, then in that case the integral, which is in this case. So, then in that case the integral 0 to infinity f x dx, which was integral from 0 to infinity dx by 1 plus x square, is convergent by mu test. So, this is one such example of mu test for this simple problem. Next we can see another example. Let's see that. So, now we can go to a bit complicated examples. So, let us consider example, and also I would like to point out that in previous class we considered an example of this type, cos x by 1 plus x square. It is better to put a square here. So, if I put a cos square x here, cos square x here, so we can test the convergence of this problem. So, not the cos x, but cos square x, so that it is rather more how to say in contrast with the comparison test of inequality type. So, the original problem should be stated as 0 to infinity cos square x by 1 plus x square dx. Then in that case it will be in contrast with the comparison test of inequality type. Now, that was just one remark or comment on my previous lecture. Next example is we test the convergence. So, I am not writing the whole statement. So, we test the convergence of 0 to infinity e to the power minus x square dx. So, we want to test the convergence of this integral here. So, let us define our function f x as e to the power minus x square, and next we want to evaluate, let us say, the limit L is equals to limit x goes to infinity. So, here in this case we have a problem at x equals to infinity, because the upper limit is infinity, and I write x to the power mu times e to the power minus x square. Now, for the time being, if I take x square instead of mu, if I take 2, then this is x square e to the power minus x square for mu equals to 2. Then this can be written as limit x goes to infinity x square by e to the power x square. And next, this one is basically infinity by infinity form, if you remember from L'Hopital rule. So, this is basically infinity by infinity form. So, I can differentiate both numerator and denominator, and this will be written as 2x divided by e to the power x square, then differentiation of x square would be 2x, and then I can differentiate the whole thing again, and this will be limit x goes to infinity 1 by e to the power x square plus x times 2x times e to the power x square. So, when x goes to infinity, this whole thing will be 1 by infinity. So, this whole thing will go to 0. So, that means the limit or the lambda of this limit is a finite number, and it is going to 0 for mu equals to 2, which is obviously greater than 1. And if it is greater than 1, then from the mu test for the convergence, we can say that the integral is convergent. So, from here we can say that integral from 0 to infinity e to the power minus x square dx is convergent by mu test. So, you see, it is always about guessing the correct value for mu. So, for what value of mu you can be able to show that the limit is finite, and if it is finite, then we have to see for what values of mu is that happening. So, if it is happening for mu greater than 1, then only the integral is convergent, like in this case, and if it is happening for mu less or equal to 1, then in that case the integral is divergent. So, choosing the correct value of mu plays an important role here. We can so there is another example where we have the divergence part. So, let us consider the integral from 0 to infinity x to the power 3 by 2 divided by 3 x square plus 5 dx. So, obviously, here we choose f x as our x to the power 3 by 2 3 x square plus 5, and since one of the limit is infinity, that is why it is an improper integral. So, let us find the limit or lambda from our mu convergence test. So, lambda is basically x to the power limit x goes to infinity, there should not be any plus here, and x to the power mu f x dx f x. So, then this is basically limit x goes to infinity. If I choose mu equals to half, then this will become x to the power half 3 times x to the power 3 by 2 divided by 3 x square plus 5 for mu equals to half, which is obviously less than 1. Then this will reduce to limit x goes to infinity x square by 3 x square plus 5, and this can be written as 1 by 3 plus 5 by x square. So, ultimately this value will be 1 by 3 for mu equals to half, which is less than 1. Now, this falls into this category, that if mu is less or equal to 1 and if the value is non-zero, then in that case the integral is divergent. So, from here we can write that. So, here we can write that integral from 0 to infinity f x dx is divergent, f x dx is divergent for mu less than 1 or by mu test. For mu less than 1 or we can write by mu test. So, that is the way we show the divergence. So, as I was saying, having this value of mu is very vital in order to ensure the convergence or divergence of the given improper integral. We will work out one last example of an integral which is very vital in integral calculus. So, the example goes like this. We will of course look into gamma function and beta function in the next class, but we see that the integral 0 to infinity x to the power n minus 1 e to the power minus x dx, which is defined as gamma function, is also an improper integral. And here I am just writing n is positive, I am not writing the range for which n is this improper integral is convergent or not. We will test its convergence now. So, for the time being, let us take n is greater than 0, and then we will see for what values of n this improper integral is convergent. So, let us test its convergence. Now, let me write I equals to integral from 0 to infinity x to the power n minus 1 e to the power minus x dx. So, first of all, if n is greater than 1, if n is greater than 1, then this integral, this integrand is defined. However, this is still an improper integral because we have one of the limits, or the upper limit as infinity. Now, when n is less than 1, then in that case this whole thing will start creating problem, because then in that case 0 will be the point of infinite discontinuity, since it will become x to the power minus something, and then that will come at the denominator, and then when x goes to, or at x equals to 0, that denominator, that particular part will be undefined. So, at x equals to 0, this function or this integrand has an infinite discontinuity. So, we can write that 0 is the only point of discontinuity for n less than 1, right. Next, let us take f x equals to x to the power n minus 1 times e to the power minus x. So, then I can write my integral I as the sum of two integrals 0 to 1 x to the power n minus 1 e to the power minus x, which is the given function f x, and then 1 to infinity f x dx. So, this one is our integral I 2, this one is our integral I 1. So, for integral I 1, we have infinite discontinuity at x equals to 0 for n is less than 1. So, let us proceed. So, convergence for I 1 at x equals to 0. So, I 1 is integral from 0 to 1 x to the power n minus 1 e to the power minus x dx. Now, in this case I choose let g x as 1 by x to the power 1 minus n. Then what will be my limit of the quotient of these two functions? So, it is 0 where we have the infinite discontinuity. I can write f x by g x, and this will be limit x going to 0 positive, f x is x to the power n minus 1 e to the power minus x times 1 by x to the power 1 minus n. So, this will be basically 1. So, e to the power minus 0. So, this will lead to 1, which is obviously non-zero. And what is this limit here, g x? I can write next. So, next this limit here, integral from 0 to 1 dx by x to the power 1 minus n. So, this integral is having infinite point of this integral has a infinite point of discontinuity, has a point of infinite discontinuity at x equals to 0. So, we can write it as limit epsilon goes to 0 positive and then 0 epsilon to 1 dx by x to the power 1 minus n, the things which we are doing in the previous classes. So, it will be fairly easy to check its convergence, and I am skipping that step and I am writing it for you that this integral converges if and only if. So, if and only if 1 minus n is less than 1. So, that means n is greater than 0. We just worked out an example like that. So, this integral converges only when n is positive. So, that means from here we can say that. So, we have a limit test, we have a limit which says that the limit is non-zero, and we were able to show that this integral converges only when n is positive. That means, the integral from 0 to 1 f x dx is convergent for n greater than 0. So, even though at x equals to 0, we had a point of infinite discontinuity for n less than 1, we can be able to show that the integral is convergent. The first subintegral, this subintegral is convergent for all n greater than 0. So, the first part is settled. Now, let us go to the convergence of I 2 at x equals to infinity, because in case of I 2, only at x equals to infinity is the improperness in the limit. The function is always defined, because even though if n is less than 1, this function will never have a point of infinite discontinuity in that interval 1 to infinity. So, our I 2 is 1 to infinity x to the power n minus 1 e to the power minus x dx, and from here we know that let us define, let f x equals to e to the power minus x to the power n minus 1 and g x equals to. So, we do not have to define, f x is actually this one. So, I can modify this a little bit. So, since f x equals to this, and let g x equals to 1 by x square. Now, from inequality, so from inequality or from our basic knowledge of inequalities, I can be able to write e to the power x is greater than x to the power n plus 1 for given n and for large value of x. Now, this can be written as e to the power minus x is less than x to the power minus n minus 1. Now, if I multiply both sides by x to the power n minus 1, then in that case this will be, since x is running from 0 to infinity, this inequality will remain unchanged, and therefore, this will be x to the power n minus 1 is times e to the power minus x is less than x to the power minus 2, which is 1 by x square. So, this is my g x, this is my f x, and obviously, this is a positive quantity. So, we have the first part of our comparison test of inequality type. Now, all we have to do is to check the value of this of this integral. So, next we have to check the values of or the convergence of this integral. So, what is the value of this integral dx by x square? So, I can be able to write limit b goes to infinity integral from 1 to b dx by x square, and then this can be written as limit b goes to infinity minus 1 by x 1 to b, and then we substitute the limit. and when b goes to infinity, the first term will go to 0. Therefore, the value of the integral would be 1. Value of the integral would be 1, which is non-zero, and this is true for all n. So, true for all n positive. So, that means I equals to, so that means I 2 equals to integral from 1 to infinity f x dx is convergent at x equals to infinity for all n greater than 0. And hence, from here we can say that I equals to I 1 plus I 2 is convergent for all n greater than 0, because I 1 is convergent for all n greater than 0 and I 2 is convergent for all n greater than 0. Therefore, their sum is convergent for all n greater than 0. That means, the given gamma function, this means that the given gamma function, which was 0 to infinity x to the power n minus 1 e to the power minus x dx is convergent at for all n greater than 0. And this is a very vital result in integral calculus, and of course, it is also our next topic in agenda. Similarly, we have an integral of type this. Let us say I equals to integral from 0 to 1 x to the power m minus 1 times 1 minus x to the power n minus 1, and we have and here we can see that 0 and 1 can be the points of discontinuities for certain values of m and n, and for this integral we can also talk about its convergence and the range for m and n for which this integral is convergent, and we will see this integral in our next chapter, because this is also in our syllabus, and this integral is called as beta function. So, this integral converges for m greater than 0 and n greater than 0. And this integral is also a type of improper integral, and because it creates some kind of infinite discontinuity at the for this integrand at the point 0 and 1, and we can proceed in the similar fashion by dividing the integral into two subintegrals, and then we look into the values of m and n for which we can talk about the convergence of this improper integral. So, we will probably do that in our next class, and I hope I was able to give you sufficient examples and theories on improper integral. We will work out few examples in your assignment sheet as well. So, thank you for today, and I look forward to your next class.